Good day everyone, here's our math challenge for today. And here's our question. Solve the following rational inequality. We have 9 raised to x plus 4 raised to x all over 6 raised to x minus 9 raised to x is greater than or equal to 5. Now, if you want to try this problem, just pause this video. We have 20 seconds and timer starts now. Time's up. Now let's answer this question together. Our goal in this question is to solve this rational inequality. Now, first thing to notice is we have 2 9 raised to x. So our first thing to do is to simplify first the left-hand side. Now, what will happen if we divide all terms by 9 raised to x? Or simply, let's multiply the left-hand side by 1 over 9 raised to x all over 1 over 9 raised to x. This is just 1. Now, let's multiply 1 over 9 raised to x to the numerator and the denominator. If we do that, we get 9 raised to x over 9 raised to x plus 4 raised to x over 9 raised to x all over 6 raised to x over 9 raised to x minus 9 raised to x over 9 raised to x. And take note that 9 raised to x over 9 raised to x is just 1. And also, 9 raised to x over 9 raised to x on the denominator is also 1. Now at this point, let's use some laws of exponent. Now if we have a raised to n over b raised to n, it is equivalent to a over b raised to the power of n. Therefore, on the numerator 6 raised to x over 9 raised to x, this can be written as 6 over 9 raised to x. And 6 raised to 9 is just 2 over 3. Now at this point, notice that 4 can be written as 2 squared and 9 can be written as 3 squared. And 2 squared raised to x can be written as 2 raised to 2x, and 3 squared raised to x can be written as 2 raised to 2x. Now we need to apply again this law of exponent. So this can be written as 2 over 3 raised to 2x. And also take note that if we have b raised to n raised to the power of m, it is equivalent to b raised to m raised to the power of n. Thus, this 2 over 3 raised to 2x can be written as 2 over 3 raised to x raised to 2. Now, to make this simple, let y be equal to 2 over 3 raised to x. Therefore, this 2 over 3 raised to x on the denominator is just y. And on the numerator, we have 2 over 3 raised to x quantity squared is just y squared. So we have now 1 plus y squared all over y minus 1 greater than or equal to 5. Now at this point, we will follow some steps to answer this rational inequality. So the first one is we need to equate this equation to 0 and then simplify. So let's do that. So we have 1 plus y squared all over y minus 1 minus 5 is greater than or equal to 0. Now let's make the denominator of 5 be equal to y minus 1. To do that, let's multiply this 5 into y minus 1 over y minus 1. Again, this is just 1. Now, 5 times y minus 1 is just 5y minus 5. Now, since we have the same denominator, therefore, we can now easily subtract these two terms. To do that, let's subtract their numerators and then copy the denominator. So this will give us 1 plus y squared minus the quantity of 5y minus 5 all over y minus 1. Now, let's simplify. Let's distribute this negative sign to the parentheses. So this will give us 1 plus y squared minus 5y plus 5. Now, 1 plus 5 will give us 6. Now, let's have our second step. Now, at this point, we're done on step number 1. Now, let's have the step number 2. So, what we're going to do is to set the numerator and denominator equal to 0 and solve. Then, the values we get are called the critical values or critical points. Now the question is, what are those critical values or critical points? The critical values of a function are where the function is undefined or equal to 0. When the numerator is equal to 0, the function is 0. When the denominator is 0, the function is undefined. Now let's start solving the critical points or the critical values of this inequality. Now first thing to do is we need to try first to factor the numerator or the denominator. And the numerator y squared minus 5y plus 6 is factorable and it can be factored as y minus 2 multiplied by y minus 3. And then what we're going to do is to equate this to 0. Now since they are equal to 0, it follows that at least one of them must be equal to 0. So we have y minus 2 equal to 0 or y minus 3 equals to 0. Now y minus 2 equal to 0, we get the value of y must be 2. And y minus 3 equal to 0, we get that the value of y must be 3. Now do the same thing on the denominator. Y minus 1 equate to 0, then solve for y. And we get that the value of y must be y equals 1. Now let's focus on these three results to solve for the value of x. Now, we know that y must be equal to 2 over 3 raised to x. So this y is just 2 over 3 raised to x, and the other 2y must be 2 over 3 raised to x. Now let's solve for the value of x. Now we have 2 over 3 raised to x equals 1. And the only value for x that makes 2 over 3 raised to x equals 1 must be x equals 0. Now how about on the other two? We have 2 over 3 raised to x equals 2 and 2 over 3 raised to x equals 3. Now take note that if we have an equation b raised to n equals a, an exponential equation, it can be written in an logarithmic equation. So we have n equals logarithm of a to the base of b. Therefore, the second equation can be written as x equals logarithm of 2 to the base of 2 over 3. And the other one is we have x equals logarithm of 3 to the base of 2 over 3. Now we're done in step number 2. Those three values are what we call the critical points or the critical values. Now let's have the third step. For the third step, we need to plot the critical value on the number line, breaking the number line into intervals. So we have a number line. We need to put these critical values in order from smallest to highest. Now, what is the equivalent value of logarithm of 2 to the base of 2 over 3? This is approximately equal to negative 1.71. While logarithm of 3 to the base of 2 over 3 is approximately equal to negative 2.71. Therefore, this is first, this is second, and x equal to 0 is the last. Now we're done in step number 3. Now let's have step number 4. So we need to take a test number from each interval and plug it into the original inequality. Now, if it makes a true statement, then the interval from which it came is in the solution. Otherwise, if it makes a false statement, then the interval from which it came is not in the solution. So again, we will use here the original inequality, and then let's have our test values. Now we need to pick a number that is greater than 0 in this interval. Therefore, any number in this interval is possible. So we will pick just 1. We can also choose 2, we can also choose 3, but we want the easiest one, so we pick 1. Now how about in this interval between negative 1.71 and 0? The easiest number in this interval is just negative 1, and the easiest number between negative 2.71 and negative 1.71 is just negative 2. And on this interval, less than negative 2.71 is we pick negative 3. Now at this point, let's substitute our test value to our original inequality, and let's see if this is a true statement or a false statement. Now replace all x with 1. So we have 9 raised to 1 plus 4 raised to 1 all over 6 raised to 1 minus 9 raised to 1. Now simplify, this will give us 14 over negative 3. And 14 over negative 3 is definitely not greater than or equal to 5. Therefore, this interval is not a solution because this statement is false. Now, let's check if x is negative 1. How about this interval? So, let's replace all x with negative 1. This becomes 9 raised to negative 1 plus 4 raised to negative 1 all over 6 raised to negative 1 minus 9 raised to negative 1. Now, simplify, and this will give us 13 over 2. Now, 13 over 2 is 6.5, and 6.5 is definitely greater than or equal to 5. Therefore, this interval is part of our solution. Now, let's continue. Let's substitute negative 2 to our original inequality. And if we do that, we can see that this interval is not part of our solution. But the third interval, if we substitute negative 3 to all x, we get that this interval is a solution to this inequality. Now at this point, we are done in step number 4. Now let's have our step number 5. In step number 5, we need also to check the endpoints of the interval. So we need to check if 0 is part of our solution, logarithm of 2 to the base of 2 over 3, and logarithm of 3 to the base of 2 over 3. Now let's start with 0. So replace all x with 0. If we do that, we can see that x equals to 0 is not part of our solution because x cannot be equal to 0. Because if x equals to 0, the denominator is just 1 minus 1. And 1 minus 1 is just 0. And we don't want to have 0 on the denominator because it is undefined. Now, how about the two endpoints? If we substitute those values to x and then evaluate, we get that logarithm of 2 to the base of 2 over 3 is okay, and logarithm of 3 to the base of 2 over 3 is also okay. Now, we're done in step number 5. Therefore, we are now ready to find the answer or the solution to this inequality. So, our solution is from negative infinity up to this point, logarithm of 3 to the base of 2 over 3, and it is counted, and it can be written in the interval notation as negative infinity, comma, logarithm of 3 to the base of 2 over 3, and then bracket. Bracket means counted, and parentheses is not counted. And another solution is from logarithm of 2 to the base of 2 over 3, and this is counted, up to 0, and 0 is not counted. So this is bracket logarithm of to the base of 2 over 3, comma, 0, and then parentheses. Why parentheses? Because 0 is not counted, and why bracket? Because logarithm of 2 to the base of 2 over 3 is counted. Now, since we have two solutions, we can combine them using the union. Therefore, this is our answer to this question. And as always, we are done.